Okay, thank you. Thank the organizers for giving me this opportunity. And good afternoon. My name is Kumar Bugga. I'm from the Jet Propulsion Laboratory. And before I launch into the actual data that we have on the lithium sulfur technology, I'd like to touch upon some of the applications where these sulfur batteries can possibly meet these missions. And for a space mission, we typically use a rechargeable battery. We don't use a primary battery for the reason that we want to extend the life of the mission. And then when you, for a rechargeable battery, of course, you need to have a source to recharge the battery, and that would be either a photovoltaic source like a PV, or it could be an RTG, which is a nuclear power source, which is a radioisotope thermoelectric generator. Then, depending on which planet we would like to explore, there are challenges. As you see, particularly if you look at on the left, if the focus is on missions that are to the outer planets, then obviously the solar radiance, solar flux, goes down almost like with the square of the distance. So it goes to such low values that we won't be able to use any PV source to outer planetary missions. In fact, the farthest that we have used is to Jupiter, and we are planning to use it for a Jupiter moon, which is like Europa. So that's where that's probably the limit for the PVs. In contrast, for missions like Neptune and Voyager and all that, we used RTG, and it's like a radioisotope that generates heat, and then we use thermoelectric materials to convert that heat into the electricity, and that's what is powering all these missions to the deep, what we call deep space planets missions. And on the same token, if you go to the near planets, inner planets like Venus and Mercury, you have much higher solar flux, and of course there are challenges in terms of temperatures. And that's what is shown on the right side. You can see that all the red that you see, for instance, if you are envisioning a mission to Venus, you are talking about temperatures anywhere close to like 475 degrees C on the surface. And on the other hand, if you go to the other side, like Europa lander, then you are talking about much lower temperatures. So you can see that depending on where we are, the challenges range in terms of temperatures. And likewise, for certain missions, we also have the radiative environments, like Jupiter and, for instance, and Neptune. We have pretty intense radiative environments that we would like to look at the tolerance of this battery to see how it survives. So with these challenges, the kind of missions that we have, typically we have missions that what we call one category is which is most benign in terms of temperatures is the orbital mission, which goes around the planetary body or even flyby. These are much like satellites, and which do not need the same rigor in terms of temperatures like the surface missions. But then the one requirement is we need extremely long cycle life. And particularly orbiters that we have for Mars, we are talking about thousands of cycles, 30,000, 10,000 cycles, 20,000 cycles, depending on how long we operate there. The flyby missions, like Europa Clipper, is one of the flyby missions that we're going to have. It's much shorter. We're talking about 100 cycles, just fly by the mission and radar, get the data. And the other set of the next category of missions, aerial missions, that they include balloons or helicopters. In fact, we have for the next Mars mission, we are going to have one Mars helicopter, and that's part of the lander. And likewise, there are several Venus balloons. These require shorter cycle life, not the other order of orbital missions. And then going down, if you talk about landers and probes, their rovers, landers, the batteries experience the same conditions as the surface, which is that is where we need either a low temperature battery if it is a Mars mission, or a high temperature battery if it's a Venus mission. And further down, you have these sample return missions where you want to collect the material, whatever that is, from those planetary bodies, and then bring it back, and they require primary batteries with long calendar life. And there are some miscellaneous like astronaut tools and equipment that also need batteries, not with long life, but typically with high energy, because you don't want to have, much like the land warriors, you don't want to have too much load on the astronaut. And the space station, of course, also needs a rechargeable battery, but it's augmented with the solar rays. And here is a it's kind of, I know it's kind of busy table, busy chart. I don't know if you can read it, but looking at the category, the first, the outer planets, what we call the missions to the faraway planets, we are talking about batteries that need at least 6 to 10 years of calendar life. That's a critical thing, particularly for a technology like lithium sulfur. It's quite a challenge. And depending on, again, the category, depending on whether it's an orbiter or it's a surface mission, we need either a cycle life or high energy. So right now, the scope is within the focused on mostly the lithium ion. It may take a while before we see anything like a lithium sulfur getting into that arena, particularly because of the challenges that we have, not only from the life, from the radiation perspective and other things. And then the inner planets, these are all these high temperature batteries that you're talking about, sodium metal chloride, lithium FeS2, these are the systems that are still being considered. We don't have, off late, we haven't had any Venus mission per se. So we can ignore that for the discussion. On the Mars missions, we are entirely focused on rechargeable batteries, lithium-ion batteries. And here too, we need low temperature applications, something like batteries that can operate down to -20, -30 degrees C. And there are some missions there which are, I would say, like a small planetary CubeSats. We have one on Mars, for instance, where a battery with high specific energy suddenly makes a lot of difference. And that's one area where we are looking at lithium sulfur as a possible application. Likewise, there is another, like any of the multi-body asteroids, for instance, if you have any surface mission, there too. And here are some of the examples that we had recently. These are all Mars type missions that we have, except the last one, which is the space station. Here we used, our approach was to use batteries made from a aerospace manufacturer within US, and these are the custom made cells. The cells range from anywhere from like 10 amp hours to 50 amp hours, depending on the mission need. And these are made, as I said, with some specific chemistry in place. In fact, we used nickel cobalt oxide chemistry with MCMB here. But the interesting thing is here we were able to utilize some of the electrolytes that were developed at JPL that are designed for the low temperature operations down to -20, -30 degrees C. And exactly in a similar fashion, there is another set of missions where we used smaller cells. These are the standard commercial 18650 cells. And the advantage here is we do not need the exotic charge management like a BMS battery management system that we need to have with the large format cells. And also these cells come with some kind of safety devices built in. So this is an advantage for us in terms of using these things. Some of the missions like SMAP, Europa Clipper, as I was talking about, we are planning to use such batteries. And there is one particular application where we thought was a perfect fit for the lithium sulfur chemistry is what we call the extravehicular activities. This is for the astronaut to come out of the spaceship and then do some science and then go back to that. And then right now with the batteries that we have, there is within 4 hours, the astronaut will have to come back and recharge the battery. Whereas if you have a battery that can have 400 watts per kilogram, in principle, you can do the 8 hours of science and then come back. And so the target being 400 watts per kilogram, we looked at next to the lithium ion, we looked at this combination of lithium-rich NMC type cathodes combined with the silicon anodes. We spent quite a bit of time on that, but those challenges are as difficult, I would say, as we see with the lithium sulfur. Right now, the focuses are more on the lithium sulfur, and a couple of people working on that, trying to do this. And then another area where this lithium sulfur can probably make some sense would be unmanned aerial vehicles and aircraft. That's something that we are looking at. And our sponsors for this particular activity is also looking at lithium sulfur as the option for the what we call the net warriors. That is right now, if you can see the line there, the one for the rechargeable. The focus in the near term is advanced lithium ion, but going up, it would be for the next few years would be lithium sulfur as the most likely option. So This, I don't have to show this again, except that I just want to reiterate that for us, for the space applications, the gravimetric energy density is more important than the volumetric. And lithium sulfur doesn't have the volumetric, no doubt. But for us, each pound matters when we fly. So from that perspective, this is still the desired chemistry for us. And this again, I'm sure there was enough discussion on this. The problems are well known with these polysulfide shuttles, and a lot of research has been going on both in terms of modifying the components at the cathode level, trying to encapsulate sulfur, trying to confine all the products within sulfur, all kinds of membranes that we are talking about, new electrolytes, be it ionic liquids or the combinations thereof. And even protected lithium. People are talking about lithium protected either with a polymeric electrolyte or a solid electrolyte to insulate it from the harmful effects of these polysulfides. So we have seen some interesting data. A lot of discussion has been going on in this conference as well. But in general, all the data that we have seen pertains to low loadings in the range of, say, 2 to 3 milligrams per square centimeter. Suddenly, I've seen some numbers here close to 5 milligrams per square centimeter, but our belief is that's not adequate to meet the energy density that we need, 400 watts per kilogram. The logic being, if we take the numbers from the lithium-ion chemistry, that today's high-energy lithium-ion cell has a loading of 30 milligrams per square centimeter. That is, per side, it's about 15 milligrams per square centimeter, combining with its 4-volt system. So we're talking about 8.7 milliwatt-hour per centimeter square. And then, and we know that today's lithium-ion chemistry can provide 250 watt-hours per kilogram. So we are talking about at least 1.5 times improvement in the specific energy. To achieve that, we need to have 13 milliwatt-hour per square centimeter from the sulfur cathode. And then again, running the numbers, so the body translates to assuming that we get like 800 milliamperes per gram, and with a composition of 65% of sulfur in the cathode. So we are talking about at least a loading of 12 milligrams per square centimeter. Actually, I've seen yesterday in the tour that I took, I've seen numbers much lower than that Oxys is shooting for right now. But granted that there is some benefit coming from the lithium anode compared to the graphite, but anything in the range of 10, 12 milligrams per square centimeter will help us get to 400 milliamps per square centimeter. And then that is a challenge based on what we know in today's lithium sulfur world. And what we did here is, this is by no means trying to do an exhaustive survey of the electrolyte, but we quickly screened out various combinations to see what is the best one. The focus one, our focus has been to develop a dense cathode, a dense, stable cathode. However, we looked at different electrolyte options here. We mainly sticking to this DME-DOL blend, and we looked at triflate as the option, imide, salt, and also we looked at some of the additives like VC, FEC. These are the standard additives that we tried, and we have seen some beneficial effect in terms of lithium-ion cells. We tried those things here, and also the combination of ionic liquid, and then our results show that the best combination, of course, in all these cases, you can see that we haven't seen this performance that we typically see with this the TFSI salt and with this simple DME-DOL blend. And so we stuck to what we have right now, which is, as I said, the blend of these two solvents with TFSI. However, we also have the standard lithium nitrate, this 0.2 molar. And then we did a lot of, we spent quite a bit of time trying to get some decent reproducible data from this lithium sulfur chemistry. And then we determined that it's kind of, we stuck to a carbon interlayer. This is based on the reports from Mandiram, UT Austin. And then we realized that a presence of a carbon layer that's between the separator and then the cathode, that seemed to provide us good reproducibility in terms of data. Without that, at least with the loadings that we are dealing with on the sulfur cathode, it was rather difficult to deal with this shuttle. So with this, with a combination of this lithium nitride and then the carbon cloth, and instead of a carbon paper, we used a carbon cloth, which is much easier to cut it to the size. And then you still see the fade is not acceptable at this loading, even though we go to like 6.2 milligrams per square centimeter. And then that's where actually we took a detour, and then we started looking at how to modify the sulfur cathode. And we know that historically that there were known metal sulfides like titanium disulfide, molybdenum disulfide, which are very reversible cathodes. And also, interestingly, they also have the voltages in the same range as the sulfur cathode. And then, as you see on the right here, top right, the conductivity of this metal sulfides is comparable, if not better, than graphite. So our approach was to replace some of the low density carbon here, which is used as a conductive diluent, replace that with a metal sulfide. And in particular, we used TiS2 and moly. And TiS2 has been reported by many people, but moly hasn't been looked at by anyone. So that actually gave us two advantages. One is it was easier for us to make the dense electrodes, and again, there is also some capacity being provided by TiS2 because it's an extremely reversible cathode system. So by adding those things, as you can see here, typically you don't see any change at all in terms of the voltage characteristics of the sulfur cell. And so we focused a little bit more on the moly. Here it is, we looked at trying to optimize how much is the MOS content that we need to have to be able to optimize the capacity. Here, we basically, in all these cases, as we vary the MOS content, we kept the carbon content the same so that there's no change in the conductive diluent. We used 20% of the carbon. But then the ratio of sulfur and MOS has been changed to get anywhere from 5% to 20% of moly in these cases. As you can see here on the right, the utilization of sulfur actually improves by virtue of having moly as part of the cathode blend. And so obviously going to much higher percentages like 20% will affect the capacity. But if you stay within that 5 to 10%, there's actually a benefit in terms of utilizing the sulfur and getting a higher specific capacity from the sulfur with this kind of combination. Here it is, we are looking at the cyclability of these electrodes, and then you can see that particularly if you stick in the range of 10 to 15% of the moly, you have a decent cycle life combined with better utilization of the sulfur in this high loading formulations. Here is a data that shows two cases. On the left, we have the TiS2, which again, keep in mind the loading we are talking about is 9 milligrams per square centimeter, and with 65% of sulfur in the cathode. And that actually translates to 4.6 milliampere per centimeter square per side. It's only because we're only coating the electrodes on one side. So if you look at a typical electrode, we are talking about twice the number, which is pretty high. And so more interestingly, what we have seen is compared to a pristine sulfur cathode, we have seen improved Coulombic efficiency with this metal sulfide blended cathode. We are seeing somewhere in the numbers of 95%, even though the electrode is fairly thick. And we started doing trying to do some understanding here, to some experiments here, trying to see what actually is happening here. And then here it is, the XRD, it's XC2, X-ray diffraction of this TiS2 at different stages. Starting down, from the down, you have a pristine uncycled material, and one discharge, and the first charge, and going all the way to second charge. You can see here the green and red shades there, they actually represent the peaks corresponding to TiS2 lithiated and delithiated phases. So there is a clear redox transition of TiS2 as you cycle the sulfur cathode back and forth. So it is indeed participating in the reaction, and then quite possibly it's helping the mediating the kinetics of sulfur cathode. And then unlike TiS2, similar set of data with moly surprisingly shows that there is no change at all in the moly. There is no lithiation and delithiation phases here. It is interestingly the effect of blending the sulfur cathode with this metal sulfide is as good as with TiS2, but there is no contribution per se in terms of capacity from moly here. And not only by way of blending it in the cathode, the metal sulfide also works as a layer. You heard this morning from Narayan is cobalt oxide working on that. Likewise here, the only difference here is that this layer of the TiS2 or moly is right on the electrode. It's coated onto the electrode. It's not separated with any separator or anything like that. But you have a thin coating of TiS2 on a simple sulfur cathode on the left here, and that actually stabilizes the unblended pristine sulfur cathode even with high enough loadings. And on the right, you can see we even tried with much higher loading and in a moly disulfide blended sulfur cathode. And then over that, we have a coating of TiS2, and that seems to give excellent cycle life as well. The coating is done by spin coating of a tiny portion of this one, or even actually it could be done like a spray coating, or even it could be doctor bladed like any other electrodes. And there is taking a clue from Ishwi's work. There's actually some understanding provided by his recent papers, where he's talking about, based on the calculations that were done, that enhanced bonding between sulfur and in the cathode to the TiS to titanium in the TiS2 being polar, and actually that binding energy seemingly is 10 times higher than what you would see with the carbon-based materials, even graphene oxide. So it's no wonder that once we have these materials in the cathode, that we have less of this shuttle effects coming from such cathodes. And moving on, we also looked at briefly at a polymer protected lithium anode. Here we looked at P-dot PEO type polymer, and then this is actually spin coated onto the lithium anode. And on the top left, you can see without any such coating with a bare lithium, you can see the onset of lithium dendrites around 50 cycles. You can see the voltage capacity is going all over because of the dendrite formation. On the right, you can see the same cathode, but with an anode which is protected with this polymer, and you can see a more stable capacity. We are still trying to optimize the amount of layers that we need to have. And moving on, we looked at the kinetics here, what actually this metal sulfide does to this, and then it looks like both in terms of the kinetics, the charge transfer as well as the diffusional kinetics seem to be the same with this metal sulfide, and much like what we would see for the baseline sulfur cathode. And then off late, we started making bigger cells, like a glass 3 electrode cells. These are cells with like 150 milliamp hour. These cells give us not only to look at the electrolyte, the changes in the electrolyte color as it cycles, but also helps us look at the individual electrode characteristics. On the top middle top, you can see the polarization is coming mostly from the sulfur cathode, a lot of hysteresis, as opposed to sulfur lithium, not showing any such. And then one last thing here I can say is on the impedance side, you can see that the one with the middle one with the carbon cloth seems to reduce the impedance. So obviously the presence of extra electrolyte seems to be helping it. And we are also looking at adopting this NMR method to quantify the polysulfides in the electrolyte. And then you saw that the TiS2 we have seen less amount of number of, we haven't really quantified in terms of the normalized to the amount of sulfur that we have, but less sulfides compared to the baseline. And then briefly, we started looking at just like we have the benefit of blending all these things with sulfides, oxides, we thought we will actually coat a separator, look at a ceramic coated separator, and then sure enough, we have seen much better performance here by just replacing a separator with a ceramic coated separator. In some cases, of course, you see some failure here around 60 cycles. To mitigate that, we thought maybe we have 2 layers, maybe one on my anode side, basically to minimize the dendrites coming from the lithium, and then the cathode side to stop the shuttles going into that. And then we seem to have better stability here. And those combining this metal sulfide blended cathodes with this separator, and then so we have seen the clear difference between on the left with a baseline cathode without any metal sulfide versus with the new separator, with this ceramic coated separator. We have seen good performance here. And keep in mind here we are talking about fairly high specific capacity, 8 milliamperes per square centimeter here. And then I would like to finally give another aspect here where people reported Michel Armand, the concentrated electrolytes where both the dendrites and both seem to be stopping here, polysulfides, and they didn't work well at room temperature, but at high temperature they seem to be doing well in 7 molar concentrations. But the interesting thing here is the Coulombic efficiency is very high, close to 1 in this case. So with that, I conclude my talk. There is interesting direction here in terms of this metal sulfide blends or coatings combined with this ceramic coated separators that we are talking about. And I would like to show the acknowledgements. This was supported by US Army, and thank Ed and Mary for that. And thank you for your time.
Thank you, Kumar. We've got time for a question or two. Are there any? Look around. Oh, we've got one over there.
Very good talk, thank you. And that's actually a pretty simple approach, right? You just coat a layer on top of electrode. And have you ever tried to coat the particle that's on surface of a sulfur particle and see if you have any relief of the polysulfide dissolution?
We can do that too. Yeah, we can actually, much like what they do in the lithium-ion world, where you coat the electrode with particles, cathode particles with all this aluminum fluoride, alumina. You can do the same thing here. But the fact that sulfur, you cannot go to much higher temperatures, it's not as easy as doing that. That's the reason we have done it.
Okay. Anyone else? In which case, thank you very much, Kumar. Kumar.